So in this chapter, we're going to be talking about the friction head loss term, which I briefly introduced in the previous chapter. So over here, you see the energy balance equation that we've derived together. And you now know high level what each term in this energy balance is, except for the frictional head loss term. And I've said that the frictional head loss term is a result of the fluid losing its energy as it travels through the piping, and it's a result of the friction and the resistance that the pipe experiences as it travels through the piping walls. And if we look at Crane's handbook, it states the following. It states that the friction head loss results from the following three items, which is fluid rubbing against the piping walls, which we already know, and obviously fluid that travels through piping components, fittings, and valves. And also it results from any changes in the direction of the flow. So if you have bends, Ys, Ts in your piping configuration, then you would have more friction head loss that you need to account for. And obviously, if you have any expanders or reducers in your piping configuration, the change in the cross-sectional area of the pipe will result in a higher friction head loss that you need to account for. And the last thing it mentions is any obstructions in the flow path. This would result in additional head loss that needs to be accounted for. So the million-dollar question is, how do you actually account for that? Because you need to if you are wanting to model your piping system. And thanks to Darcy, we have an equation that we could use whereby the frictional head loss term is equal to, if we're talking about a pipe, for instance, it's equal to the friction factor of the pipe. And the friction factor is a dimensionless number, and I'll be talking extensively about what that means and how do you actually calculate that in later slides. So the Darcy equation is the friction factor multiplied by the length of the pipe spool that the fluid travels in, divided by the internal diameter of the pipe, multiplied by the velocity of the fluid squared, divided by 2 times the gravitational constant. Now, there's another way that you could represent the Darcy equation, which in my opinion is a lot more useful. And that is if you represent the Darcy equation in terms of the resistance coefficient. So you could see that the terms inside this bracket can also be referred to as the resistance coefficient. And so if you rewrite the Darcy equation, this final form is the one that we would be using, which is the frictional head loss is equal to the resistance coefficient, which here is represented as capital K, multiplied by the fluid's velocity squared, divided by 2 times the gravitational constant. And essentially, the resistance coefficient is a more useful way in terms of calculating the friction head loss, and I'll tell you why in the next slide. So expressing the Darcy equation in terms of the resistance coefficient is more convenient because you'll find published data values for valves, fittings, and components available online based on experiments. And also at the same time, you would reach out to the supplier and the vendor of the particular fitting and component that you want to calculate the frictional head loss for, and they would be able to provide you with an equation that you could use to calculate the resistance coefficient, or a chart, a graph that you could use to find what the resistance coefficient would be when you use it for your particular application. It's important to know that the resistance coefficient is a dimensionless number. And if we look at the friction head loss term, the units for it, we said previously in chapter 2 that it must match the other terms in the energy balance equation in terms of units. So the velocity squared would be meters per second squared, and the gravity units is meters per second squared. And if you cancel the meters squared with the meters at the bottom and the second squared with the second squared, you have the units would be of the friction head loss would be in meters. And we know that it must be the case so that it's consistent with the energy balance that we've seen. And similarly, you can convert the friction head loss term from units of meters to units of pressure, the same way you would with the other terms in the energy balance if you multiply it with gravity and the fluid's density that you're using. And I want to highlight this particular paragraph from the Crane's Handbook because I think it's important for you to know. And they state that the resistance coefficient values would theoretically be the same and constant for all sizes of a given design or line of valves and fittings, only if the sizes were geometrically similar. However, it's very difficult. However, geometric similarity is seldom, if ever, achieved because the design of valves and fittings is dictated by manufacturing economies, standards, structural strength, and other considerations. In other words, if you have a particular valve component or fitting that you're installing in your piping configuration, the best thing that you should do is you should contact the supplier or even look at their catalog for the different fittings they have and see which fitting that you are wanting to use in your piping system and see what the resistance coefficient value of that would be in order to calculate your frictional head loss. Now, the other thing you could do is you could look for approximations and estimates that are available online for you to use. And there's extensive published data for many valves, fittings, and components that are only estimates. However, they're good starting points for you to use while you are assessing a piping system. And I'll show you some examples of that in the next slide.